Among the great inventions to transform our world, one circles high above the rest. Born as a testbed to develop weapons of mass destruction,
It showed that they could fire missiles all the way to the States.
our lives have come to depend on them. From global communication
They've made the world a smaller place.
to transforming navigation,
The GPS system means you can know where you are, no matter where you are on the globe.
from watching to predicting the weather,
We've gotten much better advanced weather warning systems, so they're literally saving lives.
and international espionage,
They were using them to spy on their rivals.
even exploring the vastness of the universe. From Earth to outer space, few things have transformed our lives like the satellite.
Satellites have literally changed the way we look at our own world and the universe beyond it.
October 4th, 1957. On a remote military site in central Kazakhstan, Soviet scientists prepare an R-7 intercontinental ballistic missile for launch. The Kremlin are using its secret payload to send a message to the United States. As the 280-ton missile reaches an altitude of 223 kilometers, it deploys the classified cargo. 19 seconds later, Soviet scientists on the ground detect faint radio signals from the world's first artificial satellite, Sputnik. At 58 centimeters in diameter and weighing just over 80 kilograms, launching this small metallic sphere becomes one of humankind's greatest scientific achievements. Crucially, Sputnik has been designed with 4 radio antennas, so it can be tracked from the ground. And its path intentionally takes it directly over the United States.
You could hear through your radios these beeps. They're the iconic beeps of the space age. But what they served to do in America was to terrify the population. Here was this Soviet technology overflying them, out of reach. They could do nothing about it.
The world listens in awe to the radio signals from this milestone scientific achievement. But the real purpose is to send the United States a military message. And the U.S. High Command receive it loud and clear. Sputnik was launched in the aftermath of the Second World War. And now, the U.S. knows that the Soviet Union can launch payloads into orbit directly over their airspace. "12 years earlier, America drops atomic bombs on the Japanese cities of Hiroshima and Nagasaki, ending the Second World War. The United States and the USSR emerge as competing post-war superpowers. The world descends into the Cold War. The United States is the first country to build the atomic bomb, but it isn't long before the USSR catches up.
It kicks off a different course of human history here because suddenly it changes the balance of power across the world. And there's only 2 so-called superpowers that have this technology, the United States of America and the Soviet Union.
A full-blown arms race emerges between the East and West, but the United States has a major advantage. They have a fleet of sophisticated high-altitude bombers to deliver their nuclear arsenal. And they know the USSR lack the capability to strike back.
The Soviet Union need a new kind of technology, something called the intercontinental ballistic missile, a rocket to carry bigger and bigger payloads, nuclear weapons, longer and longer distances.
Soviet military scientists begin developing the R-7 rocket and plan to make sure that America knows that the balance of power has shifted.
You have to remember, this is, the Cold War. People are genuinely afraid nuclear bombs could mean the end of the world. Now, the thing that keeps them feeling safe is that the Soviets don't have a way of delivering this bomb, until, of course, they do.
Sputnik announced that the Soviet Union had the means to strike back.
And now we know that our biggest enemy has the means, the missiles, to do this.
Alarm bells ring in the Pentagon.
When they put Sputnik up there, essentially being traveled on what is kind of a ballistic missile, it showed that they have the capability of going that high up, and that high up is also about how high up you need to go if you want to. You can see what I'm talking about here. They could fire missiles that would be able to travel all the way from the USSR to the States.
At this point, the Americans feel that they need to react and react strongly when it comes to their own sort of satellite and missile program, because, yeah, they both have the bomb, but now their arch enemy has a very clear means of delivering it, and they've told them in no uncertain terms by launching Sputnik.
The USA need to catch up. The space race has begun. And satellites will be on the front line. Keeping satellites in orbit isn't easy.
It's a real challenge to get things into orbit, to put something in space and make sure it actually stays there. So there are two factors. You've got speed and you've got gravity.
Satellites actually stay in orbit by getting the balance right between the gravitational pull of the Earth and the speed at which the satellite is moving. Get that speed wrong and you could send a satellite just shooting out into space. Get it right and you could have a satellite that's orbiting the Earth constantly.
Kind of like if you were to swing a ball on a piece of string around your head. The ball would fly off if the string disappeared, but the string is keeping it going in that circle. And that string is analogous to the force of gravity.
So in exactly the same way that the planets orbit around the sun, the moon orbits around the Earth, the same laws determine exactly how satellites orbit our planet.
The first stage is to find a reliable way to launch the satellites into space. In an unexpected move, they turned to the Navy, setting them the challenge of launching the United States' first satellite. 6th of December, 1957. In front of the world's press, the U.S. Navy prepares to launch their Vanguard rocket. It rises to an altitude of 1 meter, then the first stage loses thrust. The decision to ask the Navy to deliver the first satellite was an odd one. The U.S. already had a rocket program, led by a man with far more expertise than the Soviet scientists. But his existence was a closely guarded secret. The U.S. missile program was led by the top Nazi rocket scientists.
They weren't just using the technology that the Nazis had developed in the V2 rocket. They were actually using the very same scientists, with Werner von Braun, who had been developing missiles for the Nazis only a decade before, now developing rocket engines for the US.
They gave him just 60 days to work out how to turn one of his existing rockets into an orbit-class rocket that can launch the United States' first satellite.
Designed with the U.S. Army, von Braun's 4-stage Jupiter-C rocket is readied for launch. On board is Explorer 1, a satellite the U.S. hoped they can place into orbit. On the 31st of January, 1958, the U.S. Army fired the 29-ton rocket's engine. At 350 kilometers above the Earth, it successfully releases Explorer 1, the United States' first ever satellite.
They finally managed to restore a bit of national pride. They showed the USSR that they're capable of developing a rocket powerful enough to put a satellite into orbit around the Earth.
But even though Explorer 1 was launched by the military, it would transform our scientific understanding of the planet.
One of the chief instruments on board was the cosmic ray detector, which had been put there on the advice of physicist James Van Allen. When they started getting the results back from this radiation detector, the results were shocking. The levels of radiation were 1,000 times higher than anyone had predicted, completely unprecedented levels.
Scientists were astonished. Just beyond the atmosphere, space is flooded with radiation. But then, at an altitude of 1,400 kilometers, something unexpected happens.
Suddenly, this enormous level of radiation completely vanished.
That would have been a huge discovery, completely unexpected at that point. It was baffling them at the time.
Physicist James Van Allen had taken the very first reading of radiation captured by the Earth's magnetic field, the magnetosphere. This blanket of radiation covering the Earth will become known as the Van Allen belt. Without it, life wouldn't exist.
As well as light, the sun is giving out a constant stream of radiation, a stream of charged particles called the solar wind. The Earth's magnetic field takes these charged particles and it deflects them mainly away from the planet entirely, but those few that do make it to Earth are funneled down into 2 points or 2 sort of circles around the magnetic poles. That's where you get the aurora borealis and the aurora australis, these beautiful green lights you can see in the night sky. But as a result, it means that our atmosphere is safe. It isn't being stripped away by the force of the solar wind.
With the discovery of the Van Allen belt, scientists realize they need to explore more of the Earth's upper atmosphere. In 1960, the United States launched SOLRAD-1.
It was trying to look at solar radiation, measuring X-rays, high-energy photons in the upper atmosphere to really see that dynamic between how the sun affects the top parts of our atmosphere.
SOLRAD-1 also had another mission. It was the US's first spy satellite.
Since the start of the Cold War, the United States has been flying secret reconnaissance missions over the USSR. But it was dangerous work. Over 200 airmen were shot down. The US needed a way to avoid Soviet radar that was identifying the American pilots. Orbiting 800 kilometers above the Earth, SOLRAD-1 is directed over Soviet territory to probe for radar blind spots.
They'd realized that the radar beams they use on the ground, they actually go all the way into space. So when the SOLRAD-1 satellite passes over the USSR, it can pick up their radar beams, find out what bandwidth they're on, and get that key information.
SOLRAD-1's secret mission is a success. The United States begin designing more sophisticated spy satellites. But it soon becomes clear that satellites have potential beyond the military. Before satellites, the distance that radio and television signals could be broadcast was severely limited. Radio waves, the electromagnetic frequency that send broadcast signals, only travel in a straight line, so range is limited by the curvature of the Earth. To send signals over the horizon, you need a chain of relay antennas and receivers. But you can't build an antenna in the middle of the ocean. Satellites offer a unique way around the horizon problem. Scientists could use them as orbiting relay stations. The early experiments are remarkably low-tech.
And one of the experiments they conducted was to launch Echo 1, which essentially was a giant reflective balloon.
Echo 1 has no electronic components. It is simply a giant orbiting mirror, bouncing radio signals over the horizon. On the 12th of August 1960, the giant mirror ball is launched into orbit aboard a 54-ton Thor Delta rocket. At an altitude of 1,600 kilometers, it releases its payload.
Once up in space, they inflated it using a chemical reaction, and then they sent some radio waves which bounced off its reflective spherical surface and sent signals back down to Earth, proving that you could send and receive radio signals from Earth. This opened the doors for so much potential in communication.
The proof of concept sees engineers develop electronic satellites that will allow them to receive and transmit radio signals from Earth. But for these pioneers, just keeping a satellite in orbit is an enormous challenge.
The problem the early satellite designers were having to overcome was the fact that satellites that are orbiting pretty close to the Earth, they're not traveling through a perfect vacuum. It's almost a vacuum, but there are still a few sort of residual air molecules slowing down the satellite as it goes around the Earth. Over time, it's not able to counteract the continuous force of gravity, and so eventually the satellite crashes back to Earth and burns up.
If scientists could push the orbit further away from the upper atmosphere, the vacuum of space should dramatically reduce drag. On July 10, 1962, they test the idea. Telstar 1 is placed into a medium Earth orbit, permanently traveling around the Earth. 2 days later, it makes history when it relays across the Atlantic Ocean the first ever live television images from a satellite.
I understand that part of today's press conference is being relayed by the Telstar communications satellite to viewers across the Atlantic, and this is another indication of the extraordinary world in which we live.
Telstar 1 ushers in a new era of global satellite television communication. The opportunities seem endless. But not long after, Telstar falls victim to the Cold War. The US military are looking for ways to shield America from nuclear attack. They know Soviet missiles would need to pass through the Van Allen radiation belt. If they can supercharge this region of space, the belt might become a defensive shield, frying the electronics of any incoming missiles. They test the theory by detonating nuclear bombs inside the Earth's magnetic belts. The theory works. The Van Allen belt becomes supercharged. And it's thought Telstar becomes the first casualty as the radiation surge destroys its electronics. Telstar was a milestone in satellite technology. Space communication is now a reality. But communication satellites still have to get past a major problem. To overcome Earth's gravitational pull, they need to travel at over 21,000 kilometers per hour. This is much faster than the Earth turns, so receivers on the ground only see the satellite for a short 20-minute window.
With communication satellites, what you want is ideally a constant line of sight out to it. You don't want it disappearing over the horizon all the time. Imagine you're trying to broadcast a major world event. You've only got a 20-minute window in order to get that message out before the satellite disappears and everyone's TV goes fuzzy.
So can you actually have a bigger window or even an infinite window?
If the satellite stays above the same spot on Earth at all times, that means you have 24-hour coverage from that satellite.
It's known as geostationary orbit.
Geostationary orbit is the right altitude to place a satellite so that its orbital period, the amount of time it takes to do a complete circle, is the same amount of time it takes the Earth to do a rotation around its axis.
And it just so happens the sweet spot is somewhere around 36,000 kilometers above the surface of the Earth. As the Earth rotates every 24 hours, so does the satellite. It does a full orbit, and that means it stays above the same spot on Earth all the time.
NASA start the SYNCOM program, short for synchronous communication, to put a satellite into geostationary orbit. Although the theory is sound, The execution requires absolute precision.
If your calculations are just a little bit wrong, your satellite ends up either shooting off into space or crashing back to Earth, both of which are very bad outcomes.
And disaster strikes NASA's first attempt when SYNCOM-1's motor misfires and they lose control of the satellite. But the astonishing benefits of geostationary orbit to global communication are too important. In August 1964, NASA launched and hit geostationary orbit.
They got a satellite called SYNCOM-3 to successfully stay in geostationary orbit above one point on Earth. And this was a landmark moment in the history of communications technology.
The dream of continuous global satellite communication and cooperation is real. The European Space Agency, China, Japan, and India will all start space programs. The number of satellites explodes. Communication satellites, Earth observatories, and international space stations all begin shaping our views and understanding of the world we live in.
It opens up the doors for an unprecedented era. Satellites made the world a smaller place. Access to ideas and information and people all of a sudden became easy, became possible.
Satellites have opened up a new world of scientific exploration, global communication, and television. And they are soon transforming our lives in unexpected ways. For most of history, humankind has been at the mercy of Mother Nature. Before the 1960s, predicting the weather was a crude science. For the early meteorologists, measuring temperature in the atmosphere was key. The first pictures of Earth from space were captured from Wernher von Braun's early rocket tests. As the rockets reached the edge of space, they captured a fleeting glimpse of the Earth. The view was too brief to be useful, but meteorologists saw the possibilities for satellites in permanent orbit.
I can't imagine the feeling of what it must have been to be a meteorologist back then, seeing the Earth from space for the first time, seeing these weather patterns from a bird's eye view, or beyond a bird's eye view, a God's eye view.
Weather is caused by the sun heating our atmosphere. If meteorologists could chart temperature changes, it could help predict the weather. But the early satellites could only see the weather, not the temperature. How do you measure temperature using a camera? NASA think they have a way. They turn to a cutting-edge piece of technology.
Anything that's got a temperature has energy in its individual atoms and molecules. They're vibrating around, and as they vibrate around, they emit radiation. Now, if you get something hot enough, like if you get some red hot molten iron, that can be vibrating hard enough to give off visible light you can actually see. But most things around us in everyday life and in the Earth's atmosphere aren't that hot. So rather than radiating in visible light, they're radiating in what's called the infrared. If you can measure the amount of infrared radiation coming off something, you can work out how hot it is.
In 1969, NASA launched a meteorological satellite, Nimbus 3, to trial the technology. On board is an infrared spectrometer to chart shifts in temperature within the Earth's atmosphere.
When they pointed it back down at the Earth and took those infrared measurements, it worked. They were able to determine those temperatures, and it allowed them to start increasing the accuracy of weather predictions.
Weather satellites use this principle with hundreds of thousands of soundings every day.
In the case of natural disasters, this can be hugely important. Infrared spectrometers are literally life-saving devices. They allow us to predict the severity of storms long before they make landfall, so you can inform people as to whether to evacuate or batten down the hatches. And in the longer term, they allow us to watch how the global climate is changing and feed that data into models, which can tell us what's going to happen to weather patterns in future, and therefore save lives that way too.
Weather satellites have made all of our lives safer. But alongside the benefits of scientific satellites, the military continue to develop them for more sinister purposes. Since the birth of the space age, the United States and Soviet Union have both been developing satellites to spy on each other. Any insight into their rivals' missile programs could prove vital. And satellites provide an ideal eye in the sky. As early as 1960, the CIA launched their first photographic reconnaissance satellite, codenamed Corona. Orbiting at 160 kilometers above the Earth, the Corona satellite is directed over Soviet territory. With an array of precision camera lenses, the satellite photographs its journey over the USSR. But working with 1960s technology presents a unique set of challenges. The CIA devised novel solutions.
They took these photos on film. So these early spy satellites would be sent up there with miles and miles of film, and they would just indiscriminately take photos of different parts of the Earth as they traveled across it. But then, how do you get that film back down to Earth?
In an age before digital imaging, the CIA have no choice but to physically retrieve the film from space. If they drop it from the satellite, could an Air Force recovery plane catch it out of the air?
So think about all the things that have to go right in order for that to actually happen successfully.
It has to deploy at the right point in its orbit so that its trajectory enters the Earth's atmosphere at the right spot.
Survive the incredibly violent re-entry into the Earth's atmosphere. The parachutes would then have to successfully deploy to slow it down enough.
The airborne rescue team have to get up and deploy to the right zone as well. They've got spies on the plane with binoculars looking for it.
To then scoop it out of the air. There's so many ways for it to go wrong. And even if everything did manage to go to plan, it would still be days or even weeks until those photos would be developed. By that point, who knows what might have changed behind the Iron Curtain?
It kind of worked. Between 1960 and 1972, over 100 Corona missions are conducted. Remarkably, more than 800,000 photographs are returned to Earth. But by the time the Corona satellite images can be scrutinized, they are already weeks out of date. The Soviet Union also recognized the problem. Their solution was to replace orbiting cameras with spies. In the initial days of the space race, the USSR set the pace. In 1961, Yuri Gagarin becomes the first human to orbit the Earth. Now they aim to put cosmonauts into orbit for extended missions.
They had had plans for space stations for decades, and they had an incredible amount of data on keeping cosmonauts, keeping humans alive beyond the Earth. This was something that they knew they could, again, beat the Americans at.
In 1974, they launch a manned space station, Salyut 3. They claim it's an orbiting Earth observatory.
They just wanted to have people up there observing the Earth and taking photos of how things changed and weather patterns and so on. But in reality, it was a spy satellite.
The Almaz spies are a major update on America's spy system.
They were there to not only direct the camera as opposed to just snapping away indiscriminately, but also they had the added bonus of being able to relay what they were seeing in real time without having to wait for the images to be sent back to Earth.
Almaz proves far more effective than the CIA's unmanned Corona satellite missions. But the Soviets worry that their cosmonaut spies are vulnerable to counterattack.
The Russians were so paranoid about getting caught out that they thought it was necessary to arm their satellites with, get this, a space cannon. I mean, we're talking real James Bond stuff here.
The 23mm cannon, designed for supersonic bombers, is adapted to fit the Salyut space station. But firing a cannon in space presents unique problems.
Newton's third law kind of gets in the way, this idea that for every force, there is an equal and opposite reaction. You know, if you stand and point a gun, you'll feel the recoil, but ultimately your feet stuck to the ground will absorb most of that force. In space, you don't have that luxury. You know, they could have actually fired on an approaching enemy and shot themselves out of orbit and off into space.
The Soviet Union had taken Cold War warriors into space. Now, the USA was about to announce a jaw-dropping escalation. Since the dawn of the Cold War, the specter of nuclear apocalypse hung over both the East and West. But Armageddon is kept at bay by a balance of power known as mutually assured destruction. Both the USA and the USSR possess an enormous arsenal of nuclear warheads and the intercontinental ballistic missiles to deliver them. But both powers know that if one side ever pushed the nuclear button, the other could react in kind. Firing the first missile would effectively be nuclear suicide, because once retaliatory missiles were airborne, the aggressor would also be doomed.
They're able to see these missiles coming towards them, but they can't stop them. All they can do is wait. Ronald Reagan was not happy about this at all.
Let me share with you a vision of the future which offers hope. What if we could intercept and destroy strategic ballistic missiles before they reached our own soil or that of our allies?
In 1983, President Ronald Reagan sets America's best and brightest the task of finding a way to render mutually assured destruction obsolete. The program will become known as the Strategic Defense Initiative.
Reagan got together his best and brightest military minds to try and come up with ways to shoot down an intercontinental ballistic missile while it's in space. That was going to mean they'd have to arm satellites.
And the weaponry they imagine mounting on board the satellites comes straight out of science fiction.
Reagan was thinking about putting laser beams on there, high-energy kinetic projectiles, potentially even nukes. I mean, this was totally outlandish, and in fact, the people thought that at the time as well. It's why they nicknamed it Star Wars. This is such an incredibly difficult task. First, you've got to identify these missiles, which are traveling really fast. You've got to be able to target them effectively. Bear in mind as well, there are going to be a ton of decoys. Once you've done all of that, then you go and try and shoot them down.
And you've got to be 100% sure that these incredibly complicated high-tech weapons are going to work first time and every time.
While the USA see the Strategic Defense Initiative as purely defensive, the USSR see it very differently.
Actually, it shifts the balance in mutually assured destruction fundamentally. The Americans could launch a first strike, and when the Russians try and retaliate, if a significant number of their warheads get intercepted, then that means that the Americans are going to win a nuclear war. This meant that the Soviets were going to have to produce their own equivalent of Star Wars. It wasn't long before the program ran out of money, and eventually the whole country ran out of money, with the Soviet Union collapsing just a few years later.
Space again becomes the arena for exploration and research, and scientists look to turn satellites outwards to explore the vastness of the universe. Since Galileo first turned his telescope towards the night sky in 1610, astronomers have struggled for a clear view of the heavens.
The Earth's atmosphere is like a big soup. There's a lot of material that distorts our view of space.
In fact, you can see this with your own naked eye. When you look at a star that's low on the horizon, you can see it twinkling. That's the Earth's atmosphere affecting it. If we could somehow get a telescope on a satellite completely outside of the Earth's atmosphere, it would be an absolute breakthrough.
NASA proposed a program to do just that. In 1983, work begins on the Large Space Telescope. Placed high above the atmosphere, it should give astronomers their first unimpeded view of distant stars solar systems, and galaxies. But to see objects billions of light years away requires the most advanced telescope ever built. NASA began designing highly sophisticated sensors to detect both visible and invisible light, all needed to see further into space than ever before. But if engineers are to incorporate these instruments into a single satellite, the Large Space Telescope needs to be very large indeed. 13 meters long, 4 meters wide, and almost 11 tons in weight. But NASA's typical satellite deployment systems won't cut it. NASA needs an entirely new craft to get it into orbit.
To get a satellite up into space of this size required a vehicle with a huge space for cargo. And that vehicle was the shuttle.
In 1972, work begins on NASA's iconic space shuttle. Uniquely, the shuttle will be able to launch, repair, and even catch and return satellites. And it's designed to carry much larger payloads, almost 30 tons with each launch. Exactly what the large telescope will need to reach space. It's an incredible technological undertaking, consisting of about 2.5 million moving parts. Crucial to the shuttle's success is its heat shield. Not only does it have to survive re-entry into the Earth's atmosphere, traveling at over 7 kilometers a second and generating temperatures of more than 1,600 degrees Celsius, each shuttle needs to do this many times over. Previous NASA craft used ablative heat shields, a protective coating of plastic resin that burned away during re-entry. But this type of disposable system won't work for the space shuttle, which is being designed for multiple missions. Instead, they line the underside with more than 25,000 ceramic composite tiles.
To line the shuttle with ceramic tiles was an incredible stroke of genius because if any of them got damaged, they could be easily replaced.
In 1981, the first space shuttle successfully launches and returns. NASA enters a new age of satellite delivery. 4 years later, the Large Space Telescope is completed, the most sophisticated optical satellite ever built. It's destined to change the way we look at the universe. And in honor of acclaimed 1920s astronomer Edwin Hubble, NASA christened it the Hubble Space Telescope. Hubble is scheduled to launch aboard the space shuttle. But before it can, after 24 successful flights, disaster strikes.
We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Control program. Roger, roll, Challenger. Good. Challenger, go and throttle up. Roger, go and throttle up.
The lives of all 7 crew are lost.
Obviously a major malfunction.
It would have had a horrific, I think, effect on anyone watching. These are people who know the people who are going up in the shuttle. These are people that have worked with them. They would have taken it very personally because A, it was their life work, B, they knew the people involved, and C, it was a failure that would have been reverberated throughout the world. It was a very public failure.
Okay, are there any forces headed out that way?
Yes, sir. DoD also reports that all soft forces have been scrambled and they are on their way.
It will be 2 years before the shuttle program resumes. In 1990, the Space Shuttle Discovery is ready for launch. Eventually, the Hubble Space Telescope gets its turn.
There would have been a huge amount of trepidation at the launch, right? Just kind of that nervous energy. Because you remember what happened, the Challenger was only a few years before. You know, that would have been very fresh in their minds.
We are go for main engine start, T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Mission Control, Houston.
All program.
To give Hubble the clearest view possible, the Space Shuttle Discovery has to launch higher than any shuttle mission before or since.
Guidance officer confirms a good roll maneuver.
4 years after the Challenger disaster, it must have been such an incredible relief to finally launch that Hubble Space Telescope.
103, 103.
Looks good.
Discovery Houston, you have a go to open the doors.
At 600 kilometers above the Earth, Hubble is released. One of the most sophisticated satellites ever launched. And Hubble starts to return the clearest views of the universe ever seen. But for astronomers, one of the most incredible moments comes over Christmas, 1995.
Astronomers decide to point the Hubble Space Telescope at what they think to be a completely empty patch of sky. We're talking like a tiny, tiny little fraction of the whole sky.
They come back 10 days later to find 3,000 galaxies. I mean, just think about that. You know, they thought there'd be nothing there, or very little.
It's the best Christmas present ever.
For the first time, a telescope observes the stars without interference from the Earth's atmosphere. The Hubble Space Telescope changes our understanding of the universe. The images sent back of distant constellations are staggering and allow astronomers to see over 13 billion light years into the past.
Because the speed of light is constant, this means that the further away you look, the further back in time you're looking. We were able to see the earliest images of the universe. We're able to look back and actually understand our cosmological history for the first time. And it blew the lid off of everything that we thought we understood about the universe.
Satellites are helping us to understand our place in the universe, even discover distant planets. But they're also able to help us navigate our own planet. 31 satellites circling over 20,000 kilometers above the Earth constantly transmit their positions. Receivers on the ground use this information to pinpoint their precise location, creating what we know as GPS, the Global Positioning System.
The GPS system means you can know where you are to an accuracy of centimeters no matter where you are on the globe.
The GPS system has also transformed shipping and air travel. It's made it so much safer because we can always keep track on where planes are, even if they're out in the middle of the ocean.
Satellites have given us global navigation, and soon, even access to information anywhere on Earth. Access to broadband requires a huge physical infrastructure. It's near impossible for users in remote areas to connect to it. But it could be possible to provide uninterrupted internet access to the entire planet. Not with land-based networks, but satellites. Elon Musk's SpaceX company is aiming to do just that. But it requires a radical new approach to the way satellites are used.
You might think, okay, well, why don't we use these geostationary satellites that can see large swathes of the planet at a given time? But you've got to remember that geostationary orbit is really far away and it takes those signals time to travel to the satellite and back again. You don't want that with your broadband. Elon Musk's solution is just to build a gigantic constellation of satellites in low Earth orbit that are going to be swarming around the planet at all times.
The project is called Starlink, a constellation of 12,000 satellites circling in low Earth orbit.
In order to get thousands of satellites into low Earth orbit, you need to be able to launch every one of those satellites as cheaply as possible.
We don't throw away planes, we reuse those, so why don't we do exactly the same for space?
They're using rockets that, rather than just being used once, are reusable. If you want to get a rocket that you've launched into space to come all the way back down to the ground, then you've got a very, very difficult problem on your hands. Firstly, you need to slow the rocket down.
You've got to be able to reignite that booster. As you descend down, you're going from a hypersonic regime to a supersonic and then transonic, and then you want to get it to at least terminal velocity.
But that's not enough. What you need to be able to do is guide that rocket into the right spot so it can land on a particular pad.
Inevitably, there were some teething problems. But eventually, they perfected the technology.
SpaceX have been using grid fins to guide the airflow around the rocket to subtly maneuver it in order to bring it down and land it vertically on a landing pad.
It's just mad.
The Falcon 9 is the first ever orbital-class rocket capable of reflight. In 2019, the first 60 of the proposed 12,000 satellites were successfully delivered into low Earth orbit. It's the most ambitious satellite program ever undertaken. Once in orbit, the constellation of satellites will allow fast broadband access to anywhere on the surface of the Earth. And satellites will soon be a regular feature around other worlds. Since 1998, the International Space Station has circled our planet in low Earth orbit. Crewed by astronauts from many countries, it serves as a research lab, allowing experiments to be conducted in microgravity. But now, NASA are looking to push the scientific boundaries further afield with the Gateway satellite, a crewed space station that will orbit the Moon. Gateway will allow astronauts to access the lunar surface to conduct scientific experiments. But NASA also hoped to use the space station as a test bed for new technologies and life support systems for their ultimate goal, sending astronauts to Mars. It's the furthest from home anyone has ever traveled, and it will be thanks to satellites.
It's amazing to think within 60 years we've gone from not being able to put things in space to having the first satellites to now our lives being, almost entirely reliant on them.
They enable us to make more accurate predictions of the weather and the climate.
With the GPS global positioning system, we can navigate much more safely and effectively.
And by placing satellites in space, astronomers can get the clearest views of the known universe. Satellites have literally changed the way we look at our own world and the way that we look at the universe beyond it.
The jet engine has transformed our lives.
The most amazing thing about jet engines is that they're a way to take a multi-hundred-ton hunk of metal full of 400 or 500 people and shove them through the air at nearly 1,000 kilometers an hour. They're an insane invention.
The invention propels millions of us to our loved ones, to exotic parts of the world. It delivers food from distant climes. But the jet is a surprisingly recent invention, revolutionizing mankind's quest to fly. Since ancient times, humans have dreamt of traveling the skies, high above the world of hassle below.
Don't we all just look up in the sky and we see birds flying and we think, I want to do that? And I think that, in an engineer's brain, starts the cogs turning where they want to find a solution.
But the runway to the skies has been long and dangerous. Our journey begins in France in 1783 with daredevil scientist Jean-François Pilatre de Rosier. This fire-breathing scientist filled his lungs with hydrogen and blew it through a flame to demonstrate its explosive dangers. But it was only when he revealed the lifting potential of hot air in a silk and paper balloon that Pilatre de Rosier made history. The first human to reach the sky, watched by 400,000 people.
We first got airborne by using the concept of density. Hot air is much less dense than cold air. It's kind of like the fact that an air bubble can rise through water because water is much more dense than air. A hot air balloon had air heated up in the balloon, and that hot air that was trapped in the balloon itself gave rise to a basket which was utilizing this idea that we could leave the ground as a result of a difference in density.
This was our first form of rudimentary flight, although there wasn't really any directionality to it. You couldn't steer, you were just at the mercy of the winds.
Inevitably, the daredevil Pilatre de Rosier came to a terrible end. On his third trip into the sky, his balloon caught fire, and he plummeted to his death. Flight is a dangerous business. Hot air balloons remained a slave to the four winds until in 1895, a German inventor named Ferdinand von Zeppelin sent air travel on a new course.
A guy called Zeppelin found a way to create some kind of steering by putting hydrogen gas, which is even lighter than hot air, it's the lightest element we have, in a big balloon that also had some steam-powered propellers.
Sturdy and maneuverable, in 1909, the first passenger airline opened for business in Germany, De Log. But the Zeppelin's lighter-than-air secret was hydrogen, the very gas that Pilatre de Rosier warned us about. In 1937, the Hindenburg revealed just how dangerous hydrogen could be. Today, balloons still run on the density difference between hot and cold air. They're considered far safer, but there remain the same problems of speed and direction. What was needed was a faster and more maneuverable way to propel us through the air and into an era of cheap and safe global travel. And the key to both lay in an invention that was already transforming travel on the ground: the motor engine. Today, motor engines power cars of incredible speed and sophistication. But step back in time, and we find a very different beast. Germany, 1885. The gasoline-fueled Benz patent motor car is considered to be the world's first automobile. But the heavy engine is totally unsuited to power a flying machine. Until two brothers find a timely solution. It's 1903 in Dayton, Ohio, USA. Orville and Wilbur Wright have designed a flying machine powered by a car engine.
And so the Wright brothers decided to try and build a combustion engine that would turn, the explosion, the mini explosion of fuel and air inside an engine and turn it into useful motion and stick that on their plane as a way of propelling it forward.
But one issue weighed them down.
Now, of course, around this time, we already had the internal combustion engine for cars. But the trouble is that these internal combustion engines were really, really heavy. You know, they're made out of steel.
Nevertheless, on the 17th of December, 1903, the Wright brothers are confident enough to carry out a test flight. Against all the odds, their flying machine gets airborne. The brothers had a trick up their sleeves. Their engine wasn't made of steel.
Aluminium had only just recently become a thing that was produced in enough quantities to actually be useful for maybe building engines.
Aluminium is one of the most abundant elements on our planet. But it was not until the late 19th century that it could be separated from other elements and used in its pure form. Since then, this lightweight but strong metal has been used for car production, bicycles, even our favorite can of drink. Aluminium was the Wright brothers' secret, the timely answer to their biggest problem: weight. An aluminium engine propelled the Wright brothers into history, and internal combustion-powered flight finally took off.
The first planes actually used the same kind of engine that you use in a car or a motorbike, an internal combustion engine, where you put the fuel into some pistons, they're going up and down, and then that linear motion can be converted into rotary motion and used to turn a propeller. And that propeller then pushes the air backwards. If the propeller is forcing the air backwards, then the propeller experiences an equal and opposite force, which pushes the propeller, and therefore the plane it's connected to, in the forward direction.
The Wright brothers' invention is still the basis of all propeller planes. The engine turns the propeller, pulling the plane through the air, while the wings use the airflow to lift the plane up. Faster and more maneuverable than a balloon, the internal combustion engine-powered propellers were the only way to fly, until the pressures of a world war led to an astonishing breakthrough. 1940s Britain. Spitfires and Messerschmitts battle for supremacy of the skies. Both Britain and Germany have engineers searching for an advantage. In top secret, Anselm Franz from Germany and Frank Whittle from Britain lead the hunt. Both men know that the greatest obstacle to faster planes is the power of the internal combustion engine.
The engine is turning propellers, and they're essentially relying on lift. They work in the same way as a wing to propel the plane forwards. There's only so much lift you can get, so they needed a different way to be able to go faster.
Military engineers in both Britain and Germany thought they could come up with a design which would allow them to move their planes faster, something that was absolutely critical if you're going to use them for warfare.
Franz and Whittle both find a way to compress the air and fuel mix without the need for heavy pistons, cylinder blocks, or crankshafts.
If you imagine a jet engine as being like a tube, then at the front of that tube you've got a turbine, which is turning and sucking in air from the surroundings. And then that tube gets narrower and narrower until you get to the combustion chamber. That's the place where the combustion happens. It's where the fuel is mixed with the air and set on fire. That means that fuel massively increases in temperature, and so it wants to expand. And that means it's forced out of the back of the jet at incredibly high speed.
And this thrust then pushes the plane forward thanks to Newton's third law, which is for every force there is an equal and opposite reaction. So this backwards force of the thrust going that way pushes the plane forward really fast.
As Allied planes erode German air superiority, the pressure is on to turn the tables. But Britain doesn't want to give up its slight advantage. The stakes are high, and both men find different approaches to the jet solution. Frank Whittle first had the idea of a jet engine while a student in the late 1920s, and has been working on it ever since.
He understood the fundamentals of lift and drag, the basic principles of aviation, and from that, he was able to deduce that if you wanted to fly further, then you needed to fly faster. And from the limitations of air density, he realized that if you want to fly faster, you needed to fly higher.
And in 1941, he delivers the first British aircraft to be powered by a jet engine, the Gloucester Whittle. Whittle seems to have won the race, but his design is underwhelming. The Whittle jet engine isn't reliable or powerful enough to propel a military aircraft. In Germany, Anselm Franz has an advantage. He can build on the work of another jet physicist, Hans von Ohain. Franz improves von Ohain's design, increasing the flow of air through his jet engine to create even more thrust. And in 1944, Germany starts production of the world's first mass-produced jet-powered airplane, the Messerschmitt Me-262 fighter plane. The Me-262 left Allied fighters for dust, but it arrives too late to save the war for Germany. But Franz's jet engine will transform the world for the better. In 1949, the first commercial jetliner takes to the air, the de Havilland Comet. Other companies around the world begin to follow suit. And by the early 1960s, civilian jets are flying everywhere. Between 1957 and 1978, Boeing delivered 725 of its first jet airliner, the 707, for commercial use. But flying on a jetliner is the preserve of the rich and famous. And soon the celebrities of the skies become known by the engine that carries them around the world.
What you had in the 60s was, literally the jet set. That's where the term comes from, which was sort of a group of people that had, the charisma and the looks and the money to not just sort of conquer the skies, which was huge, but to make the world smaller.
The stars who belong to the exclusive jet set include the likes of Frank Sinatra and Brigitte Bardot. And they revel in the jet set name and the glamour.
You'd have to kind of come down the stairs, right? So it was almost like a catwalk, and you have all those glamorous photos of kind of the wind blowing up and people smiling and waving. It was a performance. It was almost like being on the red carpet.
But soon the jet plane is supersized, and overnight, the door to global travel is opened up to everyone. The jumbo jet is first flown commercially in 1970, and its massively increased cabin capacity sees prices drop and passenger numbers increase.
All of a sudden, air travel goes from something that's for the very select few to something that's accessible to everyone. And this means that we can take holidays, that the average family can visit new destinations, see different cultures, experience new things. And again, we kind of see a huge sort of leap forward culturally in our society.
Suddenly, the world is our oyster. Ordinary folks can holiday in exotic, faraway places. And the expanded horizons have a dramatic impact on life back home.
And all of a sudden, our high street changes. Because what happens then? Because we can travel and we've tried this amazing food called a kebab or a curry or something else in a different part of the world, we then bring it back and we cook it for our friends.
Today, high-volume travel around the world contributes hugely to the global economy. Every year, airlines fly nearly 4.5 billion passengers on almost 45 million flights around the globe. But the jet engine has also transformed the world in more sinister ways. From the 1950s onwards, the skies fill with military as well as passenger planes. And one country dominates: the United States of America. In late 1945, just months after the end of World War II, a new conflict begins. And the United States designs a jet that can deliver nuclear bombs to faraway targets in Europe and Asia before returning to the US. Dubbed the Cold War by British writer George Orwell, in the New World Order, the two great global superpowers, the capitalist United States and the communist Soviet Union, are pitted against each other. This is a deep-seated ideological battle that threatens the world with total annihilation.
And this was a really frightening time for people. You have to remember, there's this very quick technological advancement. Now we have the ability to obliterate the world, and people are told this, right? There's public announcements on the TV and radio.
We all know the atomic bomb is very dangerous.
Explaining how the end will look if it comes, and constantly feeling like you're, this idea of a few minutes to midnight, that you're very close to everything being taken away.
Films are broadcast in the UK and the USA, advising people how to survive the destructive power of a nuclear bomb. And drills are organized in schools to show pupils how to protect themselves.
What are you supposed to do when you see the flash?
It means you're in a constant sense of anxiety, that you're constantly looking, over your shoulder. You're constantly worrying about what, that next step is going to be. And during that period of the Cold War, that's what it always was, that at any day, in any hour, in any minute, it could be the end.
A true mammoth of the sky, largest and fastest jet bomber in the world.
But the very engine that can deliver the bomb becomes the best safeguard against it ever being used. In 1957, the U.S. Air Force demonstrates the reach of its new B-52 Stratofortress nuclear bomber by flying them non-stop around the world. The capability of the B-52 acts as a nuclear deterrent in the increasingly hostile standoff. This time, the threat of war sees the jet engine propelled to new heights.
During the Cold War, the US and the USSR were thinking of ways of attacking one another. They saw the limitations with the plane. Planes can be shot down. Is there some way we can send a warhead without having people with it? And the problem is that these two countries are quite far apart. So if you want that trajectory, you actually have to pass out of the atmosphere into space. And that means things like the jet engine can't be used because there is not enough air there for propellant to make it work. So you need to create a missile that takes the air with it.
The V-2 rocket, a flying laboratory.
The V-2 rocket, developed by the Germans late in World War II, proves that once launched, ballistic missiles are almost impossible to stop. As the Second World War ends, both the Russians and the Americans rush to exploit the Germans' engineering superiority. the USA captures V2 creator Wernher von Braun and his team. And the Soviet Union also snaps up large numbers of captured German V2 scientists for its own research program. Both sides invest huge amounts to take the jet engine to the next level. The Russians are the first to prove that jet power can take us into space. In what seems like the blink of an eye, they supersize the German V2. On the 4th of October, 1957, the Soviets used the world's first jet-powered intercontinental ballistic missile to launch Sputnik. A gigantic jet engine powers mankind's first satellite far beyond the Earth's atmosphere.
Sputnik hurtles its way into space to make a date with history that heralds the dawn of a new era.
But how can a jet engine work in the vacuum of space? The trick is to carry oxygen in liquid form.
The ballistic missile, it mixes your two fuels. So you have liquid oxygen and a more conventional propellant. They get mixed together and ignited. Similarly to in the jet engine, right? That causes a great expansion, which is directed out of the back, and that produces the thrust at incredible speeds that propels the rocket along. And so actually, well, on its path, it's being propelled up to incredible speeds on this part, and then just following the laws of gravity to reach its target.
The jet engines that launch Sputnik give the rocket a range of 8,800 kilometers, easily able to deliver a nuclear warhead to targets in the United States. America is gripped by Sputnik mania. And it urgently needs to show the Russians it can strike back. Their first attempt is a dismal failure. But scientists work around the clock to ensure a success next time round.
Okay, we'll start now. Any fuel loading? Once you're clear for launch, clear to launch.
And on the 31st of January, 1958, American jet engines fire Explorer 1 into orbit around the Earth.
In plain language, the United States was in the space business along with the Russians, and Explorer 1 was the beginning.
The U.S. space exploration program continues apace, overseen by the National Aeronautics and Space Administration, NASA, formed later that year. But the Russians score another first, when on the 12th of April 1961, cosmonaut Yuri Gagarin becomes the first person to orbit Earth. People on Earth could see Gagarin, and he could see Earth. Soviet jet engines are behind a string of impressive firsts. So the U.S. has to work hard to regain the propaganda initiative. In May 1961, President John F. Kennedy makes a bold public promise.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
But Kennedy also wants to take the heat out of the rising fear of nuclear war.
And we have vowed that we shall not see it governed by a hostile flag of conquest, but by a banner of freedom and peace. We have vowed that we shall not see space filled with weapons of mass destruction, but with instruments of knowledge and understanding.
And so the pressure is on America's engineers to rise to the challenge.
We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
If you want to get people to the moon, the crucial thing you need is speed. Because what you need to do is get those humans moving fast enough that they can escape the enormous force of gravity trying to pull them back down to the surface of the Earth.
You need to get up to 40,000 kilometers an hour, which is utterly immense. The problem also being, to be able to do that, you need a lot of fuel. So you're taking a lot of oxygen and a lot of your other fuel together to mix it. But the more fuel you take, the more mass you have. That means you have to have even more fuel. So it's a really big technical challenge that took a long time to be able to come up with a solution.
A solution is finally here. A 3-stage rocket with enough thrust to get humans to the moon.
The first rocket that was big enough and powerful enough to manage this was the Saturn V, still the largest rocket ever built. It was over 100 meters high, weighed about 3,000 tons, and about 90% of that weight was just fuel and liquid oxygen to propel that thing into space.
On the 16th of July, 1969, U.S. astronauts Neil Armstrong, Edwin Buzz Aldrin, and Michael Collins set off on the Apollo 11 mission. Five jet engines launched the rocket from the ground, and a further 6 give it the speed it needs to escape the Earth's gravity. On the 20th of July, yet another jet engine delivers the astronauts safely to the surface, allowing Armstrong to become the first man to walk on the moon. He famously describes the moment.
It's one small step for man, one giant leap for mankind.
The jet has delivered beyond its inventors' wildest dreams.
So in 1969, the jet engine that's up until this point allowed us to kind of explore our world, all of a sudden allows us to leave our world. So we have those iconic images of being able to look down at our planet. Now, I think there's nothing more unifying than feeling that you're a small part of something bigger. So to see those first images would have felt that as a race, as a human race, we had not only conquered the skies, but conquered the future.
With the moonwalk, the United States wrestles back the initiative from the Soviets. Astronauts are hailed as the ultimate American heroes, and the Soviets are left in their wake. Jets have taken humankind into space. But are there any limits to the speeds jet engines can achieve on Earth? The rocket-powered American plane, the Bell X-1, was the first craft to travel faster than the speed of sound.
Tracking the sound barrier in level flight.
Piloted by U.S. Air Force Captain Chuck Yeager in October 1947, this research plane is drop-launched from the bomb bay of a B-29 bomber over the Mojave Desert in California.
He entered a rocket plane, the XS-1, and was dropped in midair. This was an historic achievement.
It later achieves an amazing 1,540 kilometers per hour at an altitude of almost 22 kilometers. Yeager names the plane Glamorous Glennis in honor of his wife. As the first generation of supersonic fighter aircraft enter service in the mid-1950s, serious work begins on designs for supersonic passenger planes. In 1962, the French and the British announced they're going into partnership to build Concorde.
100 passengers and all their baggage from London to New York in 3 hours. That's the promise of the Concorde, the joint Anglo-French supersonic aircraft.
The engineers create a streamlined plane to deal with the massive wind resistance.
If you want to fly supersonically, then the challenge really is the aircraft design. Rather than these straight wings, you need oblique wings, you need swept wings. And that allows you to fly faster and faster. And you've got to have a much finer fuselage to make sure that you can handle the supersonic speed.
But the Americans don't want the Europeans to own the field. So they fight back to preserve their own aviation industry. In 1966, Boeing wins a U.S. government contract to build a supersonic plane that carries 3 times more passengers than Concorde. But the Boeing 2707 project is short-lived. The plug is pulled due to rising costs and the lack of a clear market. It was an ominous warning that goes unheeded. Meanwhile, Soviet intelligence is instructed to find out as much as possible about the Anglo-French prototypes. The USSR miraculously unveils a rival supersonic plane, the Tupolev Tu-144. The plane looks so much like the Concorde that it's dubbed the Concordski in the Western press.
Russia's supersonic jet, Concordski.
Inevitably, the head of the Paris office of the Soviet airline Aeroflot is arrested for acquiring classified information about Concorde. Nevertheless, Concordski scores a massive propaganda coup when in June 1969, it becomes the first civilian plane to exceed the speed of sound, 4 months ahead of the Anglo-French Concorde.
But you've got to admire the Russians' timing, getting Concordski into the air just before Concorde.
4 years later, the Soviet dream is dashed when Concordski crashes in France.
Then suddenly, without warning, the Concordski is in trouble.
It's pulled from service after a further crash. Meanwhile, the French and the British have been forging ahead with their supersonic project.
The Concorde, first commercial supersonic transport, has its public debut at Toulouse in southern France.
And it's a moment of huge anticipation as Concorde prepares for its maiden flight.
There at the end of the runway is Concorde 001.
135. Nose come up to 20 degrees, she's airborne. She flies. Concorde flies.
320 degrees, 3 nœuds.
Allô, Blagnac, ici Concorde.
This sleek aircraft is safely tested at some 70 airports on 6 continents.
In every country it has visited, Concorde has proved to be an irresistible magnet to the crowd.
It makes its maiden transatlantic crossing in 1973. By 1976, it's finally ready to take passengers. Concorde has a maximum cruising speed of 2,179 kilometers per hour, double the speed of sound. And it slashes the journey time to the Big Apple to around 3 hours. But as the plane forces its way through the air, it creates a problem.
As the plane moves faster and faster, as it gets closer to the speed of sound, those pressure waves in front of it start to bunch up. And if the plane actually makes it to the speed of sound or moves beyond, then those pressure waves are piled right on top of each other, creating a really large disturbance in the atmosphere. And that's what you hear as a sonic boom. When you cross the sound barrier in an aircraft, you actually don't notice anything changing at all, but the changes are very significant for anyone who happens to be nearby when you go through this barrier. They'll hear an enormous, deafening sonic boom, which can even smash windows of houses on the ground.
This loud, thunder-like sonic boom leads to angry protests.
Environmental groups have fought through the courts to have the flights banned.
And Concorde is indeed banned from flying over the United States and other countries.
Concorde executives know that the ban in America is virtually the end of the road.
It has cost the British and French a staggering $1.4 billion to design and develop it, 10 times more than planned. And iconic though Concorde is, it seems it's not meant to fly. A crash in France in the year 2000, which kills all 109 people on board and 4 on the ground, signals the end of this glamorous but expensive status symbol. Both the French and the British finally throw in the towel in 2003. When the British Airways Concordes return home for the final time, the crowds gather for an emotional farewell. Despite the demise of supersonic travel, passenger numbers on planes traveling at subsonic speeds have soared. The jet engine has effectively shrunk our planet. But an even more urgent problem threatens its future. Global warming. And air traffic is a massive contributor of atmospheric CO2. As icebergs melt and freak weather events wreck people's homes, what are today's jet experts doing to avert the nightmare of global warming? The race is on to design a new jet engine that doesn't guzzle so much gas. Down on the ground, we have electric cars. Could electricity power a plane?
There are a number of people looking at what we call urban air mobility or flying taxis, which are battery-powered, driving either fans or propellers.
This compact flying saucer lookalike is being developed as a 5-seater air taxi, which you'll soon be able to hail with an Uber-style app on your phone. It has 36 electric jet engines, so it can take off and land vertically in cities and travel up to 300 kilometers in an hour. The aim is to provide intercity travel that is less expensive and kinder to the environment, with 0 emissions. It can go 5 times faster than a car and produces less noise than a motorbike. In 2015, this all-electric two-engine plane scored a historic first, taking off by its own power and crossing the English Channel.
It was almost perfect, and of course I feel good. The job is done now, yeah.
But we are still some way off using electricity to power a large passenger jet, such as this Airbus 350 XWB. This can carry up to 350 people over longer distances. But its engines burn around 7 tons of fuel per hour.
If I were to replace that amount of fuel with batteries, rather than 7 tons of kerosene, I would need 250 tons of batteries. So that gives you a scale, a magnitude of the challenge that we face.
250 tons is a lot to carry, to fly for an hour. But frequent flyers need not despair. Engineers have another way to make flying greener. And they have cutting-edge tools to help them, including assisted and virtual reality.
Today, the engineers have a plethora of tools which allows them to take a 3D representation of their engine, literally move it around with their hands, undo parts of it, look inside it, and literally take off component by component. You can walk inside the engine, if you like, and look at how it relates to the aircraft and make sure there are no clashes and it fits perfectly. So it's a very powerful design tool to allow you to really understand what happens during the early stages and de-risk it before you start making the expensive hardware.
So the ground is more fertile than ever before for engineers working on complex systems, exploiting revolutionary new inventions.
The future for the jet engine is really to get further by being more efficient and to get there faster. The next revolutionary step comes with new types of engine.
The synergetic air-breathing rocket engine, Sabre, is being developed by Reaction Engines with support from BAE Systems for a new generation of flying machines. It will deliver the fuel efficiency of a jet engine with the power and high-speed ability of a rocket, and it will propel both air and spacecraft.
It's a hydrogen-fueled engine, but still requires oxygen when operating within the atmosphere. But the beauty about this particular engine is that the aircraft can fly at 100,000 feet, which is more than twice as high as any civil airliner. So the atmosphere is very, very thin, and that means there's very little oxygen. So what we do is we use a novel system called a pre-cooler, which rapidly cools down that really high temperature air which is hitting the aircraft. And the reason why we do that is because we need the air to be cold, because if it's cold, it's compressed. And that means there's a lot of oxygen now, and we can use that to combine with the hydrogen fuel on board in order to produce quite a potent jet out of the back of the aircraft, and that drives us to very high speeds.
Conventional jet engines can only power aircraft up to 3 times the speed of sound, Mach 3. But this pre-cooled high-oxygen design can operate at Mach 5, 2.5 times as fast as Concorde. The Sabre engine would make it possible to fly from London to Australia in 4.5 hours. And space travel would be revolutionized by a reusable spacecraft using the engine.
It means we can go anytime into space rather than having to build a rocket each time, having to perhaps recover the components of a rocket to service them, rebuild them, and put them into space. So we're looking forwards to a situation where we can go into space at perhaps less than a day's notice, as opposed to many months or even years.
We've traveled a long way from Pilatre de Rosier's hot air balloon and the Wright brothers' first propeller airplane having a spacecraft ready to go at short notice would make the Apollo program that got a man on the moon look distinctly old hat. Adventurous tourists would be able to hop on board to be whisked away to other planets. A voyage into space that we never would have thought possible.
The jet engine has revolutionized the way that we view the world. It's taken this once enormous planet and turned it into this little thing that we can cross in just a few hours.
Part of being human is wondering what's up in the sky. So the ability to conquer the skies, the ability to conquer where we think divinity lies, is, I think, the ultimate expression of human ingenuity.
How did we get from this to this? This story is one of extraordinary thrills.
World champion!
Driven by a revolution in electronics and a transformation of the arts.
Fortune favors the infamous.
To create a business worth over $100 billion. With some of the biggest names in sports and entertainment all wanting a piece of the action. Conceived in our darkest hours by our most brilliant scientists, they helped us win victory, and they've been stimulating our imaginations and creativity ever since. But which came first, the computer or the game? Believe it or not, without gaming, computers would not be what they are today.
Right from the very beginning of the development of computers, games were really at the heart of what was driving the technology forward.
Science and video games have always shared a symbiotic relationship. There's so much good that video games can do for us.
The origins of this incredible partnership go back to a time when evil was on the brink of triumph. The Second World War. Britain is in mortal danger.
500 German bombers and Messerschmitt fighters roared over the English coast. German bombers broke through London's defenses and reached the center of the city.
Germany is in the ascendancy. It has conquered most of Europe, and its dominance seems to be rooted in its groundbreaking technology.
In the Second World War, one of the biggest assets was cryptography, the ability to send messages that the other side couldn't read. And the Germans gained a huge advantage with the invention of the Enigma machine.
Enigma, portable coding machines that automatically convert vital messages into unintelligible strings of letters. They protect the Nazis' most important secrets, especially the missions of their most potent weapon, the U-boat.
They might send the coordinates of a submarine which would have moved a couple of hours later. And that means the British intelligence needed to work out a very fast way to crack these codes and find out what messages were being sent.
To escape Nazi bombers, the nation's secret code-breaking center has been relocated to Bletchley Park, a country house where a brilliant young mathematician, Alan Turing, reports on the very first day Britain entered the war.
One of the hardest things about cracking the Enigma code is the sheer number of combinations that the machine could be set to. There were these dials on the machine, and depending on how you set them up, it would completely change the encryption. And because that was changed by the Germans on a regular basis, it meant that you had to be able to crack that code very quickly. That meant that it was far too slow to try and crack these codes by hand. And so British intelligence decided to use computers. And these aren't the computers that we have today, tiny little silicon microchips. They were huge, clunking, whirring electromechanical machines. But nonetheless, they were much, much quicker than humans at trying every possible combination of codes and working out how that Enigma machine was set up.
The computer Turing designed was a game changer. Cracking Nazi codes, it helped to swing the war in Britain's favor. But in 1942, the German Navy improved their Enigma machines. Now it could take up to 100 times as long to decrypt each day's U-boat messages. Bletchley Park's computers were overwhelmed. It took nearly a year to design faster code-breaking computers, regain the advantage, and pave the way for an Allied victory.
It was not only for the people of Britain, but for the people of the world. Hitler had lost the battle.
But with the Nazis defeated, new enemies emerge, with new codes to crack. Just a few years later, the Cold War began.
These are today's Soviet weapons, long-distance supersonic missile carriers.
Even more powerful computers were needed to crack Soviet codes. But how do you know if your computers were getting smarter? Alan Turing had a crazy idea. What if you could challenge your computer to a battle of wits?
Turing was one of the first people to suggest that one way to do this is to get it to play games.
Because if a computer could understand the rules of the game and then learn to play it perhaps even better than a human, that could be a first step towards making a machine that was intelligent.
There was just one problem.
It was so advanced, this piece of software that he envisaged, that no computer could run it.
Although Turing talked about this quite a lot, he never actually programmed a computer game. He had a chess simulation game, but it was never actually enacted on a computer.
And so the first game of his program, called Champ, was actually played with him taking the role of computer. He would manually go through, try and work out these hundreds of potential moves. It would take him 30 minutes per turn, and then he'd move the piece as the computer would have moved it.
But when Turing's chess program played a human, the program lost.
So it turned out that even Turing's computer program wasn't smart enough to outwit a smart human.
Turing's dream would have to wait. His brilliant idea of a game-playing computer was beyond the technology of the time. He never lived to see his program running on a computer. That would take an electronic revolution. 1950s America. There's a growing demand to store and process information. Electronic computers are getting more powerful and easier to use. Then in 1961, Boston's Massachusetts Institute of Technology gets its hands on the very latest model, the PDP-1. It comes with 9 kilobytes of memory, a keyboard to type in commands, and crucially, a monitor which could display images. MIT students immediately grasp its potential, not to transform business or manufacturing, but to transform gaming.
The first ever computer game was called Space War, and it was developed by a team of guys at MIT who loved sci-fi movies, and so they developed this game where spaceships would move around on the screen and they would fight each other.
You're kind of rotating around a gravitational center, and you've got to try and shoot the other ship whilst not kind of getting sucked into the black hole in the middle of the screen. People were completely enamored with it. They loved it.
And the game soon spread to other universities.
One of the big things about Space War is that this was a shareable computer game. Computers in those days didn't have CD drives or USB or even floppy disk. They had paper tape. And that meant that by giving this punch tape to somebody else, they would have a copy of the program that would allow them to run the game on their own computer. There's just one problem, and that's that there's only a handful of these computers in the entire world, and they cost $120,000. That's about $1 million in today's money. So this wasn't just something that you'd have in your garden shed.
The PDP-1 transformed computing. It was used to create the first word processor and some of the earliest electronic music. But commercially it flopped. Only around 50 were ever made. Computer games seemed destined to remain an obscure hobby for a handful of college nerds. But they would inspire a young man from Utah, and history would be rewritten. The USA in the 1960s. Americans have more money and more leisure time than ever before.
Introducing the American way of life on the threshold of the golden 60s. Comfort, recreation, fun. These are the ultimate desires of today, tomorrow, and the years ahead of us.
It's a boom time for drive-in movie theaters and bowling alleys. And the new phenomenon, teenagers are demanding to be entertained. Pinball machines are hugely popular, but one student in Utah believed he could do much, much better.
The thing that's interesting about Nolan Bushnell is the way that he recognized the potential to do something with computer games that nobody else had.
While studying electrical engineering at the University of Utah, Nolan Bushnell came across Space War. It was a life-changing moment.
He was sort of blown away by this game and wanted to try and clone it and see if it was possible to get it out there so that more people could enjoy it.
During a summer job at an amusement park near Salt Lake City, he realized how he could bring his game to the masses.
These were arcades with like pinball machines and all the things like that. But he saw how people were really interested in getting engaged with playing those machines and thought, could you take the computer game that I've managed to play at university and put that into an arcade? But would people be interested in a slot-controlled computer game?
Bushnell was sure that they would, if the game's machine could be made cheaply enough. A recent university graduate, Bushnell decided to build his own dedicated gaming computer from borrowed parts from his new employer, who didn't seem to mind.
Really, this first idea of trying to get a computer game down to a point where it was small enough and it was cheap enough that you could monetize it. You could stick it in a bar or in an airport or in a hotel somewhere. People could put money into it and play a game for a bit, and you could make money off that.
The game Nolan Bushnell came up with was Computer Space. At less than $1,000, it was affordable, and its design certainly made a big impression.
It's like this weird, elongated, bright thumb with a computer screen where your nails should be, and this like really weird sort of Buck Rogers-style control panel in front of it. So, I don't know, it must have looked like something completely crazy when you saw it.
But his design for the world's first coin-operated video game was less than ideal.
Nobody was quite sure when they approached the cabinet what they were meant to do with it.
It was a little nerdy for the average user, seeing as its manual was multiple pages long and basically required a computer science degree to even start to understand.
1,500 computer space machines were built, but they didn't all sell. Nolan Bushnell's gaming revolution seemed to have stalled.
Despite the lack of success of computer space, he wasn't deterred. And in fact, he went away and started his own computer game company.
And the first game that they really tried to have a go at was much, much simpler. Very, very simple tennis game that he set his engineers the task of developing.
Bushnell was determined to learn from his earlier mistake. Simplicity was the key.
Instead of using a multi-page manual, he created one line of instructions. Avoid missing ball for high score. Beautifully simple and to the point.
To be honest, you didn't even need those. It was obvious. Don't let the ball go away, just keep on hitting it backwards and forwards.
There is really nothing to it. It's just a single dial and you go up or down, and that's it. There's no fat on that at all.
The simple game got a simple name, and it wasn't long before Bushnell got an unmistakable sign that Pong was going to be a big hit.
They would stick them in bars in the local area near the developers, and there was one in particular where the developers got called up pretty quickly after they put it in, and the bar owners said that this thing's broken and people can't do anything with it. It's just not working.
He discovered the problem with it was that actually it had broken down because it had too many quarters in it. It was so popular that everyone had jammed the machine, desperately putting money in to play it.
I think that was probably the first point that they went, hang on, I think we're onto something here.
Bar owners loved Pong for one simple reason. It made money. At least 4 times as much revenue as a pinball machine.
It was a massive success.
Pong turned Nolan Bushnell's fledgling company into a household name, Atari. And with 19,000 sales, Pong also kick-started a whole new kind of business, arcade computer games. Unlike their pinball rivals, as tastes changed, so could the games.
An arcade game like pinball, as lovely as it is, it's very determined by the actual physical machinery of the unit, right? And that's hard to change. Whereas a computer game is software. All you need to do is upload that software and maybe just change the artwork on it, and then bam, you have a new game.
And this flexibility would prove a lifesaver for gaming companies. In 1981, the Japanese company Nintendo took a big risk trying to break into the US computer games market.
They'd got this game, Radar Scope, which had done very well in Japan. It's second only to, I think, Pac-Man at that time. But they were setting up in the US and had taken a very big gamble. I think it was something like 3,000 units they'd shipped all the way to America.
Once it was over there, they realised it wasn't doing quite as well as they'd hoped. They weren't able to sell them.
Normally, Nintendo would have gone bankrupt, but the software revolution was about to prove its worth.
By that point, the hardware was effectively generic, so you had got a monitor and you'd got a cabinet and a joystick and some buttons.
So instead, they just repurposed them, stuck new stickers on them, and uploaded a new game and shipped that out. And that game we all know and love. It's called Donkey Kong and was a huge success.
150,000 Donkey Kong arcade games were sold, making Nintendo $1.75 billion. Donkey Kong was revolutionary for other reasons too. This was a computer game with a story to tell. A little carpenter watches in horror as his girlfriend is kidnapped by a gorilla. The player must help the carpenter rescue her.
I was interested in the idea of narrative. Actually, it doesn't just have to be about shoot things and high score. We can tell a story.
And the name of the carpenter? Mario. But you probably know him better as a plumber. He's since appeared in over 200 computer games. Computer games had gone from cottage industry to big business in just a few years. By 1982, the arcade game industry was earning $27 billion. It was the golden age of arcade games, and everyone had their favorites.
My favourite was the Teenage Mutant Ninja Turtles arcade game. It was a really hard game. You're going around, you're just getting beaten up by everybody.
Mortal Kombat was a big one. I had my first kiss behind a Mortal Kombat arcade cabinet.
So even though the graphics didn't look so good at the time, I have very happy memories of those sorts of games.
Happy players spent money. And arcade owners fell back on old tricks from the gambling industry to keep the quarters flowing.
In many ways, these arcades employed the same techniques that casinos do in terms of making sure you stay there as long as possible. Now, what do when we want someone to kind of lose track of time? Well, we avoid having things like clocks around. We make sure that there's no natural sunlight. We make sure that there's a lot of stimulus in terms of sound and color, because obviously the longer you play, the more kind of coins you put in that slot.
But despite the trickery, after just a few years, the arcades started losing their appeal. The fundamental problem was lack of choice.
We couldn't just have everything. We had whatever was at the place that was nearest when we'd got 10p's in our pocket. Or it was what the one was that was in your local chip shop.
By the mid-'80s, arcade game revenue had fallen by 2/3 from its peak in 1982. The golden age was over. Arcades faced a new challenge, a revolution in home entertainment, the computer games console.
The first games console was called the Magnavox Odyssey. What a delightfully archaic name that is.
And it was revolutionary because for the first time it took games out of the arcade and into the home. But the thing is, it was still rather clunky.
It could only had enough power to generate, say, 1 or 2 pixels either side of the screen and then maybe a blob in the middle to represent a ball.
So in order to make it into any kind of entertaining game, it came with plastic overlays which you'd stick onto the screen to turn this into some kind of adventure.
If you wanted to play hockey, then you put a transparent plastic overlay on the screen that made it look like a hockey pitch. If you wanted to play football, you'd just swap it out for that.
It didn't have sound or color, and it couldn't be updated. The Odyssey's electronics were too primitive to run software.
Instead of just loading and saving new data onto the machine, you were basically inserting a whole new circuit board, almost an entire new computer, specially designed to play a particular game.
And yet for 3 years, the Magnavox Odyssey was unchallenged, the only home video game system in existence. More than 300,000 were sold. It was a tantalizing glimpse of the future.
And really, it set up a whole genre of devices. It plugged into your TV, you could play different games on it. This was a precursor of every games console that's come since.
The idea that you could actually interact with your television was mind-blowing.
Like Alan Turing's chess program, the Magnavox Odyssey was a brilliant idea, but too clever for the technology of its time. The 1970s was the decade when the electronic revolution really took off. Computers were now processing data through tens of thousands of electrical circuits using transistors. A breakthrough in miniaturizing them meant you could pack lots of transistors onto tiny slivers of silicon. The result was the microprocessor, a computer on a single chip.
This is a general-purpose computing unit. It can do addition, subtraction, mathematics, and it's programmable, so you can tell it what you want to do.
Microprocessors allowed companies like Atari to create arcade games small enough to fit into the home.
So a few years later, a new device comes on the market, the Atari 2600, built by our old friend Nolan Bushnell. And this was a truly revolutionary device. Now you could just go out and buy a game, which came on this sort of cartridge that you plugged in, and off you went.
Atari uniquely were very well placed at that point to be the people that did that, because the name Atari was synonymous with arcades and gaming.
Yet despite its advanced technology, the 2600 didn't sell well. Atari's chief executive believed the problem wasn't the tech. The company's games simply weren't good enough.
He was aware that popular arcade games like Space Invaders and so on were a huge hit with the public already. So he figured he could buy the license for those kind of games and put them on his console.
The availability of this on the Atari platform propelled its sales to new heights.
I think that's the first time that you had a third-party game sold on somebody else's platform. That was huge.
Space Invaders helped Atari sell 30 million consoles over the next 15 years. It was a gold mine. So other electronics companies tried to muscle in with their own games consoles.
So soon we started seeing more and more consoles appearing every year. And this was thanks to the fact that sort of computing technology was exploding.
And each company insisted that their technology was better than anyone else's.
You've got Nintendo saying they've got Mode 7 graphics where they can rotate and scale 2D things to look like 3D. Fundamentally, it is about it's about realism, it's about colour, it's about speed, it's about excitement, it's about giving you the most overwhelming experience that technology can offer you at that point.
This was the era of Sony's PlayStation 2, the most popular console of all time. It sold more than 150 million units. Entertainment was being transformed.
I was definitely a games console kind of girl. It was the thrill of challenging myself that I think got me hooked.
Platforming, I think, was the thing that I was sort of most into at that stage, and you know, they were really fun games, even though, you know, quite simple.
I always wanted Nintendos for some reason, because I always thought they were a bit better. Sorry, Sega.
I think Mario is better than Sonic. I feel I've reached that decision after playing both. Mario's definitely better than Sonic. It is.
But in the 1980s, a new foe challenges the console makers. It wasn't a rival company. It was a totally different machine. In 1981, the computer giant IBM created its personal computer, the PC, the first machine they specifically designed for the home, not business. Consoles were no longer the only game in town.
You could probably have bought a computer for comparable or less money that did an awful lot more and was probably more powerful than the console.
Video games console, once you bought it, that was it. You couldn't really do anything with it. You couldn't upgrade it. You couldn't update the operating system or anything like that.
IBM electrified the market by revealing the PC's technical specifications. Owners could pimp their PCs with powerful graphics and sound cards made by other manufacturers. Games designers suddenly had an exciting new platform for their ideas.
The people that were into PC gaming were constantly upgrading their own machines to be able to play the game, so it was not only better for the developers in terms of making a game, but the games could always be more cutting edge. And it always seemed to be more games as well for a PC, so why wouldn't you be a PC gamer?
If every home in the US has a computer, but maybe only 10% of the homes have a games console, then it kind of makes more sense to go for the PC market than the games console market. There's a lot more potential for getting a lot more money.
As games moved into millions more homes, designers used the psychological insights first learned in the arcades to make their products more compelling.
Now, obviously, they couldn't control the home environment, but what they could control were the rewards that you were given that made sure that you stayed on. Our biochemistry, actually, is designed for that.
The key is dopamine, a chemical in our brains critical to motivation, arousal, and reward. Humans are powerfully drawn to anything that releases dopamine.
There's that human desire for an instant return. It's that dopamine hit. You win the race, or you explode your spaceship, or you upgrade into a better spaceship, or you get more credits. It's a dopamine hit. The human desire for a dopamine hit, that instant return on our kind of investment in time, is something that becomes very addictive.
Game designers are brilliant because, they understand the human psyche very, very well.
From the moment computers entered the home, a whole new generation of gamers were hooked. There were games for every taste. You could control colorful characters across perilous platforms.
I absolutely loved Chucky Egg.
I just remember as well, like when his little legs would go like that, it would like it had some great sound effects.
You could become god of your own world. Control simulated humans. Adventure through strange and unsettling worlds.
I remember a game called Blood Money where you're in a submarine and you're going around shooting alien fish to get money. It was really weird.
You could manage a premiership football team, fly a fighter jet, or drive your very first car.
Outrun, I think, was one of the first I can really remember spending a lot of time on.
You could even unleash your inner Caesar or Napoleon to conquer virtual worlds. But real enthusiasts didn't want to just play games, they wanted to make them as well. And since PCs could understand programming languages like BASIC, they could.
And the first game I can remember playing on it was something called Eatum 2. It was a bit like Pac-Man. I thought was most exciting about it was that you could design your own map. So you could go into a separate program, you could put in walls, and you could control where the monsters would appear and where the power-ups were.
I think we had a games typing book where you type in entire games. And so that was a lesson in patience.
It'd take way longer to write the game than you'd ever play on it, but it was really teaching me about how logic and programming works, which is something I do like all the time now in physics. So my sort of gaming experience, I think, has sort of influenced my life.
The ability to create your own games in your own home was extraordinary. And by the 1980s, gaming would enter a brave new world, a world where no nerd had ever ventured before.
The new world of mobile gaming all started with the Game Boy. Suddenly, you had computer gaming in the palm of your hand.
It was cheap, it was affordable, and it had the brand of Nintendo at the time when Nintendo were undisputably the gods of gaming.
It's just this idea that you could, just pick up a console and switch it on and it'd be ready wherever you were, and you could just play games for 5 minutes. That was completely alien at that time.
But what was the magic ingredient was the game that Nintendo chose. It was the marriage of this handheld device that was extremely convenient, mixed with a game that was almost addictive, Tetris. Everyone could play it.
In 1996, at the ripe old age of 7, the Game Boy got a new lease of life from another game changer, Pokemon. It became one of the biggest game franchises of all time. Game Boy wasn't the first or last, but few handheld consoles could challenge the gaming Goliath. Nintendo sold nearly 120 million of them during its extraordinarily long production life.
It's hard to describe how awesome it was. I mean, it was one of those things that everybody had, and I really wanted one. And my mum teased me relentlessly about it. She was like, no, you can't. I eventually got one for my birthday, and I think I nearly passed out with excitement.
After it bowed out, both Sony and Nintendo created other handhelds based on newer technology. But the real success story wasn't a gaming machine at all. And it was all down to the genius of one man, Steve Jobs, when his pioneering company Apple kickstarted the smartphone revolution. The huge popularity of the powerful iPhone and the rival smartphones that followed meant the handheld console became less relevant. In 1989, the year the Game Boy was launched, revenue from mobile gaming was a mere $1 billion. 30 years later, it had soared to nearly $70 billion, half of the total gaming market, and almost all of it earned from smartphones. But beyond thrilling us, gaming can now help cure us.
What we're starting to see nowadays, just over the past 2 or 3 years or so, is scientists starting to really think about how they can use video games as their labs, so their own kind of digital, online, experimental environments where they can collect data.
In Sea Hero Quest, researchers collect information about how people navigate. That data becomes a valuable diagnostic tool.
You have a fantastical seafaring dad who's starting to lose his mind, and he's lost his journal of all of his amazing adventures from when he was younger. They've been scattered to the seas. So you as his son have got to go out and try and collect all of these memories from his journal. So you've got to figure out where all the boys are on this map. Once you've had time to memorize it, then you get into the game. Now, behind all of that is a massive experiment. So what's happening is that a team based at UCL and the University of East Anglia are collecting data on where you go, how you navigate around that environment, what you do when you go in the right direction, and critically what you do when you go in the wrong direction. And all of it is in order to understand what goes wrong in that sense in terms of spatial navigation in the case of things like Alzheimer's disease.
More than 4 million people from every country in the world have played Sea Hero Quest, producing over 100 years' worth of data. It's helping scientists understand much more clearly when and how our navigation ability declines with normal aging. But the reason why people anywhere on the planet can join this huge online experiment is down to the extraordinary vision of an obscure British scientist. In the 1980s, only one group of people had access to computer networks linked to like-minded gamers: students at the biggest universities. They alone could go beyond the single-player experience and play with others.
So you could be playing someone completely other side of the country to you that you likely you've never met and maybe never ever will meet.
But you couldn't enjoy the thrill of space war over these rather slow networks. The first online games were less visual and more collaborative.
They were text-based games, so you kind of say things like, go north, and it'll move you north.
Players may have had to write instructions like take, look, or attack to play in this shared world. But they knew the concept had a future.
You had this shared universe where you could do whatever you wanted. You could fight other people, or you could join communities of like-minded people and just socialize with them.
That ability, even that early, to share a gaming experience with somebody else, not with you, it's mind-blowing.
So it's not a massive jump of logic or of imagination to think, why can't I do it with somebody on the other side of the world?
So when the World Wide Web came in, that allowed people from anywhere in the world at any time to participate in these same games.
In 1990, Tim Berners-Lee invented the key components of the World Wide Web. These include the first web browser, a system for identifying computers anywhere in the world, and HTML, a language allowing anyone to create a web page. Games designers use these web tools and combine them with the latest cutting-edge graphics originally developed for PC games. As a result, game playing went global. One of the biggest was World of Warcraft, which launched online in 2004 and is now in its 7th expansion.
Beautiful, ephemeral, unattainable. I didn't listen. No one listened.
There was this incredible, at the time it felt like an endless world that you could explore. This really vast experience where you can just bump into other people all the time. In a kind of real-time setting where you've got an actual 3D character who can wave and talk. Then you can also create guilds of like-minded people who want to do that particular thing. Maybe they want to raid and they want to kind of take down high-level bosses, or maybe they just want to faff around and chat to each other. There's such a vast, rich story there that, you know, like I say, I've been playing it for 10 years and I've still not got through it all.
Online games create immersive worlds where people can play together and make real, lasting friendships.
Minecraft was the one for me. I mean, I spent thousands of hours just existing in this world with friends I'd only met through a friend on the internet, building a world together. It's intoxicating. We'd set projects and decide, okay, we're going to go to that place and build this thing, and we're going to gather the resources and do it together. And there's something different about that.
You know, there's this caricature of the kid playing alone at home and, you know, mom saying, you know, go out with your friends and play. There's no go out with your friends and play. I could be playing with my friends at the other side of the world. I could be playing with my best friend who I've never met before on the other side of the world, because that's what that sense of community is a big part of it.
I don't really think that we should be thinking about in terms of whether they're better or worse than real-world friendships, but they're just different and they have their own benefits.
I built a theme park. So we literally had a working roller coaster, and there was an archery thing where if you shot 3 targets within a minute, you won a little prize that came out of a machine. There was a log flume. That sort of the grandness of creating an entire theme park in a game.
It may look simple, but it's collaboration that's led to 175 million sales, making Minecraft the best-selling game of all time.
There's loads of games I really enjoy, but there's nothing that's ever got me like Minecraft. Yeah, that's a real place that I've been, even though it isn't.
The problem, I think, becomes when you feel only comfortable connecting in the online world and you retreat from the you know, the real world, as it were. That is an issue, and I think there needs to be some kind of honesty about that.
But what if you don't have to choose between the online and the real world? What if you can do real things in a virtual world?
You get to be a part of an entirely different world. You get to have experiences like you couldn't imagine. There's no boundaries anymore. There's no things like physics, or you could be flying a dragon, or you could be going underwater, you could be going into space and doing a spacewalk. You could literally be doing anything you imagine with no boundaries. And that's what's so exciting with VR.
The origins of virtual reality can be traced at least as far back as the 1950s. Air forces began using ever more realistic flight simulators so their pilots could learn to fly without putting themselves or their cutting-edge aircraft at any risk. 21st century technology takes the flight simulator to ever greater levels of realism. But pilots aren't the only ones now learning in a virtual world.
VR for surgery and medical training is enormously valuable, and it is now being used around the globe. So there are medical schools now, particularly in the Far East, that use this. So the old-fashioned idea about showing medical students surgery on, you know, real-life bodies, don't need to do that anymore. You can have a virtual classroom of as many people as you want, watching a skilled surgeon demonstrate all the anatomy of the human body using a VR replica, showing all the complexities, rotating the viewpoint up and down, and I would hazard a guess that that's the way surgery will almost always be taught in the future.
But it was the military who had the most resources to create sophisticated simulations, and the biggest need for them. In the past, training American soldiers with live ammunition led to disastrous accidents. 1 in 6 of the soldiers who died in Vietnam were not killed by the enemy, but in training. So in 2012, after 5 years of development, American soldiers began virtual training.
What the system is designed to do is expose soldiers to different types of scenarios or environments that they might encounter downrange, whether it be deserts or mount environments. They will get a general feel to what they might be able to see downrange.
Let's go, squad leader. You got everybody back? Keep moving, keep moving. Let's go, let's get somebody up on the high ground.
They've even developed a program for dog handlers to hone their skills by working with virtual dogs. It could help them find real roadside bombs. And with the continued targeting of civilian and military personnel, it serves a vital current need. As well as allowing professional soldiers to train in complete safety, virtual reality can also help us better understand the experience of our fellow civilians, caught up against their will in conflict.
We help to produce this interactive, immersive piece that puts you into the shoes of a family in Syria, in the middle of the Syrian conflict. And it lets you see how families are living at the moment, this many years into the war. And you have this very physical, very human connection, this emotional connection to another person. But then something terrible happens. The room essentially gets raided by some local militia. And you have to make a decision of what the family does. So you're given two very stark choices. Do you run or do you hide? And then you get to choose, you see something happen, and again, usually it's very bleak. And then at the end of your chosen narrative, you're given a simple message from the Red Cross to explain that they're one of the few people left there. And essentially the message being that for these families, there is no right choice. And doing that in virtual reality, it doesn't allow you to escape from that reality. You're in that world, everywhere you look, it's around you. And that's something very impactful, which hits people very heavily emotionally.
The power of empathy and the ability to work together in teams are important aspects of the appeal of computer games. But sometimes, we just can't resist our desire to compete.
We often think of video games as a very isolating experience. It's somebody doing something on their own, but actually, since the 1960s, since those early video games arcades machines, and even previous to that, games have been multiplayer by design.
Gaming is more fun with other people. Play is a thing that you do with people, whatever form play takes. And those earliest games, like Space War and Pong, you have the thrill of a human opponent. I get to beat you, and that is more compelling than beating a computer. If I play you 1,000 times, it will be different 1,000 times. If I learn the way a computer behaves, I can beat it every time once I know how to beat it.
So in the 80s, Atari ran a massive Space Invaders tournament.
Space Invaders had just been released on Atari's pioneering console, the 2600. Players competed in 5 regional events across America.
I think 10,000 people took part in it in the end, and there was a big finals event held in New York.
But even in this pioneering contest, the consoles couldn't be linked together. The players weren't fighting each other, only the Space Invaders. It was another decade before game designers could give players the dubious pleasure of killing each other. Welcome to the world of the first-person shooter.
Doom was one of the first games that introduced the deathmatch, the free-for-all. You have your level, your game arena, and you're free to roam around, but you are, completely on your own. And the point is that everybody else is an opponent, and you need to kill as many people as possible. It was insanely addictive, incredibly fun, but incredibly competitive at the same time, almost like a sport.
But it wasn't the creators of Doom who turned the deathmatch into a global online phenomenon.
The original Doom had multiplayer that was only local, right? You had to be on the same network, and that was it.
It was actually the fans themselves that decided to incorporate it and sort of hack it so that you could play it across the whole internet. You could play against anyone around the world.
In the late 1990s, online gaming was growing fast. But to get the best experience, you needed the fastest connection. And at the time, South Korea was the most connected country on the planet.
they were going through this sort of financial crisis at the time, and the government's response was to pour money into technology infrastructure. So South Korea has some of the best kind of internet networks and infrastructure in the world.
So when the online strategy game StarCraft was launched in 1998, it was a huge hit in South Korea, selling 2 million copies there in its first 3 years. Professional players formed teams and started playing against each other in ever bigger competitions, to ever bigger crowds, in ever bigger arenas.
You know, the gaming world, very much like the athletics world, has its superstars, has its amazing athletes.
You can buy merchandise, you can buy t-shirts with the team's names on, and you can buy a hot dog for 10 quid, and then you can go and sit down. And for 10 hours a day, you can sit and watch hour-long gaming tournaments back to back.
If you're not in that world, it feels like a subculture, but it's a huge subculture. We're not talking, you know, a few hundred people here. We're talking literally millions of people. You know, we know that there's people that absolutely have amazing careers doing this, that are poster boys and girls doing this. People are celebrities in their own right.
If you've ever seen football covered, it's that. They know the individual players, and they know their team, and they're there to support them, but they're all playing a video game instead.
Spectators at these esports events are as enthusiastic as any other sports fans.
They're enjoying watching high-level gameplay, so seeing people able to do things that you wouldn't be able to do yourself when you play that game, because in the same way that you can appreciate a really good footballer because you know how hard it is to kick a ball well, you can really appreciate a squad of players working together well, or individually doing things that would be beyond your ability.
And just like conventional sports, millions of viewers watch the big events at home. Not on TV, but online, where designers have adapted their games for spectators.
You could control an in-game camera that you could fly around a game that you'd played previously, so you could get really good action shots from different viewpoints. That was quite groundbreaking when it came out in the early 2000s. So the big esports-orientated games that broadcast live online have these systems whereby somebody who's effectively a director and a video cameraman, basically, can figure out what the best shots will be live during these sports matches, in the same way that you'd have those sorts of people recording a live football match or a live hockey match.
Prize funds in the biggest competitions are now reaching tens of millions of dollars. Top players can earn hundreds of thousands of dollars a year or more.
You see people who are, you know, teenagers who are getting paid so much money to play computer games. I mean, back when I was a teenager, I'd love to be able to do that. Wasn't a thing.
In 2018, the global esports market was worth $900 million, with a worldwide audience of 380 million viewers. The traditional sporting world is waking up to the huge opportunities now available in esports.
Then what we started to see was more investment from big multi-conglomerate sports ventures, so people who own big NFL teams or NBA teams in the US, starting to buy into esports teams as well.
Even if the games themselves are a bit different to football and cricket.
There's something about putting everybody in an environment and making them fight for their lives, and that's the essence of what makes those sorts of things so exciting, is the stakes. It's death. It's death.
From their early days as a bold dream conjured up in the mind of one of our greatest thinkers, the invention of computer games has transformed our world.
I think there's a lot of good things that have come out of gaming, right? You know, you have a new sense of community, you have, this push on technology, you have the ability for, kids and young people to connect with each other around the world.
I think what computer games have given us is a new way of actually telling stories.
You can be immersed in that story, you can be part of it, and your decisions that you make within that game can change how the story ends. What gaming has provided is an entirely new sort of artistic, cultural medium.
The depth for human creativity in terms of computer games is endless.
It's given rise to, to new sports, as it were. It's given rise to new ways of connecting, communicating. It's given rise to new identities.
There was a time when children were condemned for the amount of time they spent in front of their computer screens. It's those early gamers that have come up with apps and all the kinds of digital technology that we have today.
Games have a huge potential to change the world looking towards the future. And I'm very excited to see what that turns out to look like.